Okay, so as next, I would like to spend a few minutes to show you a simple example about the primitive joints. And the example that I would like to introduce you is the one you can see in this slide. Let me change the view for you guys. So this one. So I have a very simple system that consists of one moving body only. And the one moving body is constrained to ground by using two primitive joints. And these two primitive joints are located in a place or points that are called P, that is here, and O, that is here. The P is from the distance, okay, maybe better to get started from the O. So the O is from the distance D along the global x-axis. So this distance is D. The P is the distance E from the global y-axis. So those are the distances where those slots are located. And I would like to create the primitive joints for this system. And now when you look at the system, you can already compute the number of degrees of freedom. And the number of degrees of freedom will be 1. And will be 1 because I have one moving body. So it's going to be 3 trenorized coordinates. And then I have 1 plus 1 primitive joints. So that's going to be 2. So it's a total of 1. So the system can move one way only. And the way it can move is like, you made the picture by yourself. So it's like sliding in a way that is like a pendulum a little bit. Little hard to describe here, but it's going along these slots, and that's how it behaves. So that's the simple mechanism. All right. Any ideas how we can describe these constraints? We will use, surprising enough, the equation that is written like this. Okay, so that's the concept again. What we're going to do with this concept? We will define the points. First, we're going to define the point O, or point P, doesn't really matter, by first traveling the body, or the origin of the body reference coordinate system, and then with help of the U-bar, we're going to reach one of the ends of the beam-like body. And once we reach the end, then we're ready to impose the constraint. And the constraint will be very simple. So we're saying that this particular location must have global x position that always have to be equal to D. That's the idea. In the similar way, we're going to travel to this end. We say that the global y direction of point B always have to be E. That's how it goes. All right? So let's see. So let's get started from the point O. So point O, we will use this equation. So first, again, we have this R vector that tells how is a translation of the body reference coordinate system. All right? So it takes us from here to here. And then we're going to use a rotation matrix to describe the orientation of the body. All right? And then we're going to use a vector U bar to travel from this coordinate system to this point. So if the length of the beam-like body is L, so how is that I can reach this end? Well, you can tell it here. So the components of vector U bar, the x component must be L divided by 2. Think about it. You here, you have to travel here to here. So the distance will be L divided by 2. And how much you have to travel to this direction? 0. Okay. So this is my equation. So now the next assignment is to impose the constraint. You have to understand that this equation here tells me how is a point O with respect to global coordinate system. So I'm ready to assign my constraint, and the constraint is that this x coordinates always have to be equal to D. How can I do it? I simply say that x have to be equal to D. All right, makes sense. Make sense? No. Would you like me to repeat it? Okay. So let's first look at the big picture again. Big picture is this. My point O is constrained. And the point O is constrained in such the way that it can do everything it wants, except it cannot translate along the global x-axis. This motion is not possible. It is constrained. And this is exactly what I wanted to constrain. So I wanted to express the position of this point using the equation that I'm very much familiar with. And then I'm going to take because this one here consists of two components that are with respect to global x and global y directions. Now I'm going to take and say that the x direction is no longer free to move, but instead it always have to have the value equal to d. Make sense? Okay, so I'm saying, okay, this is my position, and this motion is no longer possible because the coordinate x must have the value d, no matter what. How can I make it happen? I can make it happen by expressing first this translation. Well, it's a variable, so I really don't know what are the numerical values. I don't really care about that. So there are Rx and Ry. So translation along the global x and y direction. All right? Then I have 2 by 2 rotation matrix that accounts the orientation of the body reference coordinate system. All right? So I'm traveling here. I'm accounting the rotations. And then I'm traveling here with help of vector u bar. Vector u bar have a value of L divided by 2 and 0. You doing this or? Okay, what is your sign to me? Please communicate with our own special language. Okay, what is your sign? Is this clear? Okay, so okay, that's my definition. And now this tells me the position O in x and y direction with respect to global coordinate system. All right. So now I'm saying that this x here is actually predefined. X is predefined to be equal to d. That's my constraint, except that is not yet my constraint. I still need to do the math. So I have to compute, I need to take this Rx. I have to compute this matrix multiplied by this vector, but it's going to be this row. So it's L multiplied by cosine theta. Then this is 0. And then d, I'm going to take it and put it in the left-hand side of the equation. This is my first constraint. Clear? One constraint equation, which eliminates the motion of this point in global x direction. It cannot do that any longer. It always has to stay in a coordinate equal to d. Okay. Clear? Are you guys depressed? Not at all. Is this too simple? A little bit. But no worries, because soon it's going to be difficult like in hell. I can tell you that. All right? So that's the first one. But not today. It's not going to be today, but within a week or two, it's going to be like something that is hard to stand with. All right? What about the P? Any ideas how we can proceed with the P? Same procedure. We always following the same procedure. So basically, we always keep on repeating this equation over and over again until you get bored. And then still we're going to repeat it. So it's repeating. Okay, this time the assignment is to go to this point here. How we can make it happen? Well, first we go the body reference coordinate system. It's going to be business as usual, so no differences there. Then we're going to account the body orientation. No differences whatsoever. It's going to be exactly the same that in the previous case. But then there's going to be vector u bar. Vector u bar must be different because I'm not going to go here, but instead I'm going to go here. How is that I can make that happen? I have to travel to minus x direction. How much? How much? L divided by 2. How much I need to travel to y direction? 0. So that's my vector u bar. And then I'm going to go and introduce the constraint. This time the constraint is imposed to global y direction. The y direction is no longer free to move, but instead it has to have a certain value. The value is defined here. So then I do the math. I will take this time this component here, this row multiplied by this vector, and then I'll take an e and put it in the left hand side of the equation. Here's my second constraint equation. Simple. Make sense? Yes, sir. Okay, so this one was the problem. Negative. Okay, that's because, if you take a close look about the axis, coordinate axis, my x-axis, positive direction is pointing this direction. So I'm not going to go the positive direction. I need to go this direction. This is a positive direction. I don't want to go there, but I want to go here. How can I go there? Minus L divided by 2. Okay. So, clear. So that's a simple primitive joint. All right? What is the purpose of the constraint equations? What's the nature of constraint equations? Here are the 4 choices. It interconnects, it combines generalized coordinates. It defines the body configuration in global coordinate system. It defines the physical dimension of the body. It defines a particle in a global coordinate system. One only is correct. What is that the constraint equations are doing for us mathematically? Joints. What is that they do? And let me change the view to this one. Okay, so is this going to be simple or what? Quite simple. Would you like to have a word with your fellow student? No need. So you absolutely positively sure what's the correct answer? Okay, so maybe I will let you, would you like to think about this, or I'm not really sure what is that you're thinking. It's very hard to read your mind. Are you like, oh my God, this is, this is like a nightmare? Are you thinking that this is so simple that I will fall asleep, or tell me, what are your thoughts? Okay. Awesome interaction. Okay. I will get back to that in a second, but before that, I will already open a new topic. The next constraint is a little more difficult. I would like to introduce you a translational joint. Translational joint is something that there is only a minor risk in a midterm exam that you have to deal with the translational joint in a very detailed mathematical level. And there's a minor risk that you have to deal with the translational joint if you go the first written exam. You know that you have 3 attempts to go to written exam. So if you decided not to do midterm exams, you can go and do final exam, which is a written exam. And you will have 3 attempts to do that. The first attempt, the first exam paper will be easy. I'm asking like, what is your name and what do you like, how is that you like about the course, and what about the weather-wise, do you like to be in Finland, these kind of questions. And then I'm asking on Revolut join and stuff like that. Second exam, I'm asking translational join and something that is ugly and difficult. And the third exam is so difficult that I cannot pass by myself. So think about it. You have these 3 choices. So it progressively becomes more and more difficult. All right? So now the next one that I would like to introduce is a translational join that combines 2 bodies together. So I have here body A. Body A is a beam-like body. This one here. And then I have box-like body, body B. And these bodies are coupled together via translational join. So it's meaning that the body B can translate, it can slide along the length of body A. It can go back and forth. If the body A rotates, body B will do the same. And again, it can slide along the length of the body A. So that's a translational join. So you need 2 constraint equations to define the constraints like this. First constraint will be extremely simple. You simply say that, okay, the initial orientation, angle theta related to body A, and angle theta related to body B, those have to be along with the certain constraints. And that's, you basically say that these have to be equal. So that's kind of the idea of your first constraint. Second constraint is a little more complicated because then you kind of prevent the relative motion between the 2 bodies. And we need a little bit of mathematics to make that happen. So that's the next assignment. And before the next assignment, let me check like how is a... Okay, so we have 74 answers. You know, I'm thinking that this time it's going to happen. Guess what? 100% success rate. 100%. Yes, 100%. You ready? So what if it is 100%? So are we going to stop the lecture? No, we're going to make a lecture longer than it is typically, because that's the way we can celebrate it. So we can make this like 4 hours lecture. Yes. So you're with me. Okay, you scared to see the results? No? Not great. Not great. Okay. Okay, so okay. So how should I make the interpretation of this? Is it like I should close it like right now, right here? Or okay. Honestly, a little bit of disappointment. Okay, so let's go back to this. Okay, let's get started from the answers that makes no sense. Okay, the only few ones mention that this defines the physical dimension of the body. Nothing to do with that. Absolutely nothing to do with that. Defines a particle in global coordinate system. Not that either. You know, the particle, we define that by using this equation. Not constraint. It's an ingredient inside of the constraint, but the constraint, idea of the constraint is what? Tell the relation between the generalized coordinates. So it's interconnect. It combines the generalized coordinates. That's the assignment of the constraints. So it is saying that, okay, these coordinates are no longer free to move, but they are coupled in a certain way. And that's because of the constraints. So this is a correct answer. Define the body configuration in a global coordinate system. Not really. Not really. But there is a point. There is a there is a little bit of sense in this. Because if we have a system that there is a 0 degrees of freedom, then you can solve the configuration based on the generalized coordinates, constraint equations. Okay, so maybe I will give you a points if you answer the B, A or B. It's still not 100%. Okay. but the correct one is A. Okay. All right, so let's go and practice this, and then I have one more in-class quiz for today, and then we're gonna stop. Okay, my first constraint was the simple one, like I explained. So you're basically saying that the orientation of the bodies have to be same all the time. Same all the time, that meaning that it have to be according to parameter C. C could be equal to 0, so it's meaning that then the orientation of the bodies will be always same. Or they may have a little bit of, angle, initial angle with respect to each other. So that's C there. Initial angle having the numerical value C. Let me explain. So if you have here beam-like body, and then the box-like body is oriented like this. Hold on. This is my body coordinate system. So this angle here is C, telling how much they are separated in a initial configuration. All right? So that's the first constraint. Second constraint is a little bit of headache. The second constraint, I have to introduce several points, and with help of those points I can define two vectors. And then using the perpendicular condition, mathematical condition, I can actually prevent the relative motion of these bodies. Because the thing is that now the B cannot move this direction without the translation of the body A. So that's what I wanted to constrain. And I can do that by introducing point O, point P, and point Q. Point O will belong to body A, point B and Q, they will belong to body B. Let me give you a better picture. So this is a situation. So I have, I'm introducing kind of like assisting points. This is the first point, and I need to change the color to make this more visible. This is my first point O. This is my second point P, and then I'm introducing one more point Q here. And now I'm defining those points using the method based on, guess what? This one. This equation will be used again. So I'm simply defining this point, and this point by using this technique. And once I have these points, then I'm able to draw the vector that connects these points together. Then I have two vectors, and perpendicular condition of two vectors. What's that? That's if I have vector x multiplied by vector y, that's going to be equal to 0. That's perpendicular condition. All right? That's what I'm going to do. You follow? You're with me? Okay. So let's make it happen. So let's define the point O in the very beginning. The point O, is defined here. So this is a point O. So to make that happen, I first have to travel the body reference coordinate system of the body A. All right? So that's this component. Then I'm accounting the orientation of the body A, 2x2 rotation matrix, and the vector U bar. I really don't know what is this numerical values. I don't care this time. So it's just the vector U bar. That's my first point. My second point, which is this one here, P, that belongs to body B. I will define that in a very same way. Again, I'm going to origin of the body B, then I will account the orientation of the body B and the vector U bar. And I don't care what is the numerical values. I don't need to know that this time. This is my first vector. The vector is called K. All right? It connects position and it connects the body A and B. So it goes from O position to B position. Here to here. Makes sense? Yes, sir.
Shouldn't it be the other way around? BP minus AO? Because I think.
So the direction?
Yeah.
You made it because of the direction?
Yeah.
We could make it in another way around as well. This doesn't really matter. Okay? But, so you say P minus O. Okay, I need to do the exercise, and I need to show this to you next week, like how we end up to have the same business. Okay? Then H. H belongs to body B. And the body H is the one that connects the P and Q. So first I will go to origin of the body B, I will account the orientation. A vector U bar takes me to P. And then I will do the same. I will go again, origin of the body B, orientation, and vector U bar. And that's because these guys will be eliminated. This will be what is that it's going to be left. Okay, that's my second vector. And then, once I take this mathematical condition, so it's h multiplied by k, that have to be equal to 0. So I have two vectors, I multiply them together. I'm saying that the results have to be equal to 0. That, by the way, is a scalar component because it's a matrix, vector multiplied by vector. So it's a scalar component that is left. So it's a one equation. Okay, it looks bad, and it is bad. But don't get confused about math. Use a symbolic math tool to solve this for you. Okay, so this is a vector h, this is a vector k, and everything is written down, and finally this is how the k and h look like, and then I simply do the math, and I'm doing a little bit of elimination. This is finally how my constraint reads. I'm using a little bit of simplification in a way, but the big picture is this. So I have two vectors, and I'm imposing the perpendicular condition. That's how I can get the second constraint equation. Makes sense? A little hard. But no worries, it's going to get harder. Soon it's going to be more difficult, way more difficult. Are you coming next week? Maybe. We'll see. Okay. Okay, so what do you guys say if I leave this without further details? Are you comfortable with this? Okay. So what are the simplifications that I did there? I mentioned, I know that this is actually in origin of the body reference coordinate system, so it allows me to use this substitution. So vector U bar associated to this point will be having 0 values, and the P is also located in the center of the body coordinate system, so I can use these values here as well. And this is how the Q is located with respect to body x-coordinate axis. So those are the simplifications that I'm able to do. And when I substitute these simplifications, this is what is left. This is my final constraint equation. Very mechanical math, nothing else. Okay. Then let's practice this. So I have two bodies that can move with respect to each other. So there is a body A and body B, and they are constrained in such the way that the body A is constrained to ground via revolute joint, and then the body A and the B are constrained together via revolute joint in a point P, and then here point Q I have primitive joint. The primitive joint prevents the motion of this particular point Q in a global y direction. So it cannot travel to that direction. Okay? What's the number of degrees of freedom? So I have two moving bodies, so it's going to be what? 6 generalized coordinates. How many constraints I have? So it's going to be 2. How many revolute joint? 1, 2, and the primitive joint. So it's 1. Okay, 1 degrees of freedom. Okay, so let's calculate the constraints for this system. So let's get started from the first body. So let's first define the constraints that is associated to this point here. And now there's a big temptation that we can take a shortcut, because we here in the very beginning, so we are in the origin of the global coordinate system when we get started in this assignment, and the constraint is imposed to this very same location. So can we make a shortcut and explain this position without traveling to body reference coordinate system? No. So we always have to go to body reference coordinate system. If you're going to take a shortcut, it's like a criminal action, not allowed. So you can do whatever you want, but never ever shortcut. You always have to go first to here, which is a body reference coordinate system, and then you come back. That's the way it goes. Always the body reference coordinate system, and then wherever you wanted to go within the body, no matter where they are located. Don't think about don't try to be smart. Don't try to make the shortcuts. They will not help you at all. Okay? So I first travel to body reference coordinate system, which is defined by this vector here. Then I will account the orientation of the body reference coordinate system by 2x2 rotation matrix. All right? Then I'm now here, and in this coordinate system, and I have to go back to the origin of the global coordinate system, which is the point O. How can I make it happen? Well, with help of vector u bar, I have to travel minus L divided by 2. Minus because if you take a close look about this one here, x-axis is pointing this direction. And I have to travel from here to here. So that's why the minus L divided by 2. Y direction, how much I have to travel this direction? 0. What's going to be my constraint? How can I say that this point O have to stay in the origin of the global coordinate system no matter what? It goes in such the way that I say that this equation have to be equal to 0, 0. Make sense? Okay, good. Okay, that gives me two constraint equations, 1 and 2. All right? Then I'm ready to move on to second one. So this time I will define the point P by using the body A, and I will do the same by using the body B. I'm simply putting these notations to be equal. That's going to be third and fourth constraint equations. And again, how can I make this happen? Again, I'm following this very familiar equation. So first, traveling the body reference coordinate system, then I will account its orientation, and then with help of vector u bar, I go wherever I need to go. Right? Makes sense? Okay, so this is body A definition, orientation of body A. Vector u bar, this time is L divided by 2 positive direction. Y direction is equal to 0. Then I will do the same with respect to body B. So I will go first here, then I will account the orientation of body B, and then with help of vector u bar, I will call this point B. Right? Vector u bar will be minus L divided by 2, 0. That gives me third and fourth constraint equations. Clear? Nice. So then final one. The final one is related to point Q, and the point Q is actually located in the axis of 0 y-axis. So I'm simply defining this point here, and then I'm saying, okay, the motion in a global y direction have to be equal to 0. So first I'm traveling the body reference coordinate system of vector of body B. Then I will account the orientation of body B, and then I will go to this point Q with help of vector u bar. It's going to be L divided by 2, 0. And then I'm saying that this y component, this component here, have to be equal to 0. It cannot move in a global y direction. You got it? So I will take this component, this matrix multiplied by this column, this row multiplied by this vector. That gives me fifth constraint equation. Nice. Okay. So what it is? So we have 8 minutes time, and it's not going to be enough to open the completely new topic, which is a Jacobian matrix and kinematic analysis. But shortly, what to expect to see next week. Okay. So kinematic analysis. So you can carry out the kinematic analysis if you have, system that have 0 degrees of freedom. So what it means. So if I have, say, hold on. a pendulum. Pendulum as it is in this configuration have how many degrees of freedom? So how many bodies? I have one body,
1 degree.
one revolution, 1 degree. Okay, so it have 1 degree in this configuration. Then I'm coming and say, okay, this 1 degree is not free to move as it wants. And it could be the way that I come and say, okay, this angle theta have to follow the equation that could be, say, theta is equal to sine time. So then the body will follow this driven constraint. So that's one additional constraint. So then I have 3 constraint equations, 3 unknowns. Remember that generalized coordinates are equal to unknowns. So those are the things we wanted to solve because they will tell us the configuration of the system. But we have all the information because we have 3 equations, 3 unknowns. So it means that we have a set of nonlinear equations and we have to solve it. How is it we can solve a set of nonlinear algebraic equations? You learned it already in junior high school. Think about it. You have a set of nonlinear algebraic equations. You have to solve it numerically. How you can make it happen? Any guesses? Okay, so you learned it in high school, not the junior high school, but the high school. Okay, you learned it in first class in mathematics in a university. So there are these iterative methods, many different methods that can be used. Have you ever heard the methods called Newton-Raphson method? Yeah, that is that we can use. So we can use that using an iterative method of Newton-Raphson. So it tells us a solution in a position level, and then we also have to solve the velocity and acceleration. All that is hidden to constraints. All that information is inside of the constraint equations. We just use a little bit of mathematical manipulation, and then we can solve it. Okay. All right. So the kinematic analysis goes is that's the way that we're first going to carry out the position analysis. Position analysis is a little bit challenging because we have to use these iterative methods, Newton-Raphson or others, but we're going to use Newton-Raphson. And with a certain number of iterations, we can get the position, accurate definition of position at certain time. Once we have position, then we can solve the velocities and acceleration. And that's the idea. That's how the whole procedure goes. You have to take care of all these stages, but step 1 is critical. Step 1 is the most difficult position level. And to make that happen, you have to write down the constraint equations, and pretty much that's all you need. Okay, so once you have constraints, everything is rest is downhill. That's what it means. Boilerplate. Okay, this is a very heavy math, so we are not getting involved to that too much today. So 4 minutes, and we have. Okay, we can close for today. And then next week we will get back to this, and I will teach you something that is called Newton-Raphson method. And in Newton-Raphson method, there is something extremely, very, very critical to learn, and that's Jacobian matrix. That's what we need to learn to find out what's the direction, how is that we can update the generalized coordinates to find the position or solution for position level. Okay. That's all for today. And this Wednesday stuff, I will ask John to send some information to you guys regarding the tutorials on Wednesday. But as what John mentioned, there will be a tutorial this Wednesday. But check out your emails. Okay? All right, and I'm going to close the recording and streaming.